Welcome to IDS-KT. Let's explore an important topic shaping the future of defense and global security. I'm the founder and director of International Defense Security and Technology, a California-based nonprofit think tank dedicated to research and analysis on global defense, security, and emerging technologies. I also serve as CEO of Interplanix LLC, a New Mexico-based company advancing satellite risk analysis, orbital debris forecasting, and space security frameworks to ensure mission assurance and resilience. Previously, I served in leadership roles at India's Defense Research and Development Organization, DRDO. Most recently as Director of the Systems Analysis, Modeling, Safety, and Quality Cluster at DRDO Headquarters, New Delhi. This channel brings you deep insights into the global security ecosystem, from geopolitics and emerging military technologies to cyber, space, and system-level analysis of tech trends and their interrelationships. Subscribe and join us as we decode the forces shaping the future of global defense and human security.
Imagine a computer so powerful it can crack today's toughest problems, things that would take classical machines years, done in seconds. That's the promise of quantum computing. But making it work isn't as simple as scaling up your average chip. These machines operate in extreme cold, just fractions of a degree above absolute zero. And in that frozen silence, something remarkable is happening. Quantum-ready cryogenic semiconductors are stepping in to make the impossible possible. Quantum bits, or qubits, don't behave like the ones and zeros we are used to. Thanks to quantum superposition and entanglement, they can perform vastly complex calculations at incredible speed. But they're fragile, just a bit of heat or electrical noise, and the whole system loses coherence. That's why quantum processors have to be kept so cold, often as low as 15 millikelvin. At those temperatures, most traditional electronics simply stop working. That's where cryogenic semiconductors come in. Unlike standard chips, these are built to operate at ultra-low temperatures without losing performance. And right now, companies around the world are racing to develop the components that will support tomorrow's quantum machines. For instance, Finland-based SemiQon recently introduced a cryogenic CMOS transistor that runs at 1 Kelvin, consumes just 0.1% of the power of conventional transistors, and can be mass-produced using standard semiconductor manufacturing. That's a huge leap towards scalable quantum systems. Intel is also making headlines with its Pando Tree chip, a cryogenic control system that operates at the same temperature range as superconducting qubits. By placing control electronics closer to the qubits, it reduces signal delay and boosts system performance, a critical step toward managing millions of qubits in one machine. And then there's the team-up of Siemens, sureCore, and SemiQon, developing cryogenic CMOS libraries and memory architectures for scalable systems. They're using advanced modeling tools and testing transistors on GlobalFoundries 22FDX platform, all part of a push to make reliable, cold-tolerant chips a reality. But not everyone is taking the cryogenic path. Quantum Computing Inc., or QCI, is betting on nanophotonics instead. Their entropy-based quantum systems don't need deep freezing or heavy shielding. They use nonlinear optics and single photons to perform quantum operations, offering scalability without the cold. Their quantum photonic vibrometer already applies these ideas to ultra-sensitive sensing and measurement. Whether it's cryogenic silicon or photonic architectures, the race is on. And both tracks might converge someday in hybrid systems that combine the best of both worlds. What's clear is this: if we want quantum computers that can transform industries from drug discovery and cryptography to national security and AI, we need the control electronics to match. Cryogenic semiconductors aren't just another tech upgrade. They're a foundational piece of the quantum puzzle. We're on the cusp of something revolutionary, and the tiniest, coldest transistors may just be the keys to unlocking it.